Bismillahirrahmanirrahim. Assalamualaikum. How are you everyone? So we're going to continue today with lecture number 14, process modeling and simulation. And now talking about just the previous chapters that we have taken, just to know where we are standing in our course. So far we have taken the model equations. Okay, so far what we have done, we have taken our model equations, and these model equations that have been taken, we represented some different systems for how does height change with time, how does concentration change with time, how does temperature change with time, and how does pressure change with time for the surge tanks. Okay, we have taken different models, right? And what we want to do, we want to take that from the time domain to the S domain, okay, where we call them transfer functions. So what do we have? We have time domains. We want to take that into the S domain. And how to do that? Doing that is through applying Laplace, okay? Through applying Laplace. And if we want to go to the other direction, where from the S domain to the time domain, we need to do Laplace inverse. So this is where we are standing now. And today what we are going to take, we are going to take this route where we are going to say that if I want to go from the time domain to the S domain, I need to do several things. First thing, what I need to do is to do a linearization step for non-linear different orderly differential equations. Okay, so this is what you need to do. So if it is already linear, that means you don't need to do this step. And when we say non-linear differential equations, that means if you are dealing with dy by dt, for example, having a term within that equation such as y squared or square root of y, that means it's going to be nonlinear. So in the case of the example that we had dh by dt, and we had in the equation square root of h, that means this is a nonlinear ordinary differential equation. Okay, so hopefully you got it. So after you do some kind of linearization, we are going to put the equation in what? In deviation formats. Okay, we are going to put them in deviation formats, and the reason we put them in deviation format is that we want to study the effect, the change of the effect, right? So the effect of the input, on the output. And how do we see the effect? So we see the effect of delta u on delta y. Rather than saying that, well, what happens if I change it from 2 to 4 and I say, what's the value? It's 4. And then I solve it. No, I say that the change is from 2 to 4. So the change is 4 minus 2, so it's 2. Or if the change is from 3 to 7. So the change here is from 7 minus 3 is 4. So we had an input of 4. So this is the way how we look at things when we deal, why we do put it in deviation format, so that we can see that effect. Okay, and after that, what we are going to do, we are going to continue with our step and apply Laplace. Okay, apply Laplace. And then we can apply Laplace inverse to go back to the solution. Okay, we go back to the solution, which is in the time domain. So these are the steps that we are going to go around for. So we already studied the Laplace and the Laplace inverse part. Okay, so we did this part here. And what we want to do now, we want to do the linearization and the deviation format. The linearization and putting in the deviation format to get the transfer functions. There's one thing that I need to mention here is that there is another method. Instead of doing it in a two-step wise, we can do that only on one step, where we do both linearization, and I'll just put that shortly. We do linearization and putting it in deviation, linearization and deviation in just one step. So that is what we are going to see here. Okay, that is what we are going to see. So we are going to use two methods, and I prefer the second one because it will be used later in advanced courses. And actually it's not because it's used also in advanced courses. In my opinion, the second method is easier, and that depends on you, which you find most suitable when you try to solve the problems. We learned actually the first one, the one at the top there, and our days the second method was not there, so that we did not study it. But now the second method is in being, so I think so we can use it. Okay, so now the questions that how do we apply the linearization step? Okay, so how do we do linearization? So we will learn now how to do linearization, and then we are going to take an application on the height of the tank. So linearization starts from the idea of having a nonlinear system and putting it into a linear system. So we do have a Taylor series for a function. A Taylor series of a function is f of a for any whatever system that I have here, or f of x, sorry. So f of x for a system is equal to f of a plus f prime of a divided by 1 factorial into x minus a plus f double prime of a into x minus a squared over 2 factorial plus, of course you already can guess, is f triple prime of a into x minus a cube over 3 factorial plus, and so on. Okay, so this just goes on. So as we are talking about linearization, right, we are talking about linearization, that means we are going to cancel all the higher order terms. The higher order terms that represent non-linear terms. And the only linear terms that we have here, is the first two terms. And these first two terms, if you look at it, this looks like an intercept, and this looks like a slope, which is the first derivative. So that is like a, and that is the difference, x minus x naught. Okay, x. So this is like, it looks like the equation of the straight line. So it makes sense for us, and it looks like a straight line. So that is like an approximation to a linear function. I know some of you will say that, well, if we delete the non-linear terms, we will have error. Yes, that's right, correct. You are definitely right. We will have an error. But we can tell you that this error is not of a bother, it's not of a concern, it's going to be small, and through experience we found out that it's enough to do this linearization step, and this small error is not very important when we go through applications, and those applications we can get a very good indication to where the level is going, or where to how the temperature is changing, without really being concerned about what? Being concerned about deleting the higher order of nonlinear terms. Okay, so we already have our equation here. We already have our equation here. So if you just want to apply, just to get the idea of how do we apply this. So if I'm going to apply this to h, square root of h, because we know that square root of h is one of the linear terms we have in our head. So if you're going to apply that to square root of h, which is one of the popular nonlinear terms, this will be square root of h at steady state. And I forgot to add here this is f of a initially, which is the f of a at the initial value, and here the initial value here that we're trying to substitute is the steady state, and here we are taking the derivative also at the steady state, all at steady state values. So if you consider here that we substituted that at steady state value plus the derivative of square root of h at steady state, it will be 1 over 2 square root of h. So the answer is 1 over square root of h. Okay, so that is the derivative of square root of h. But because we said that it's at steady state, so the h will be at steady state. Okay, into x minus x. So x is inside the function. Okay, x is inside the function, and a is the initial condition, which is the initial condition of that x. Okay, which means that x, which is inside the function, which is h in this case, minus the initial condition of that h, which is the steady state value. Okay, so beautiful. So we got our form. So this is the form that we have for linearizing square root of h. And how do you know that this is linearized? Look at, if we substitute instead of this nonlinear term, we substitute that. We can see that h is a linear term, it's h to the power 1. Whereas those values, these are just constant. Okay, these are constant values, so don't worry about them. They are not variables, so they are not counted as non-linear terms. No. So we have only a linear term here sitting, which is h minus hs. Beautiful. And actually this makes us happier that we already know how to do the linearization for square root of h, which we will use in a moment. Okay, so that is the first popular nonlinear term, and I will write something at the top there just to remember. So what I'm trying to do here, I'm looking at the popular nonlinear terms. Okay, the popular nonlinear terms. So this is what I'm trying to do here. Okay, well, someone would ask me, like, if it is linear and I'm going to do a linearization for a linear term, what will happen? Just for the sake of what you have asked, if you're going to do this, it's going to be something like that. So h, for example, we want to linearize this. So it is equal to initially h at steady state plus the derivative of h is 1 into what's inside is itself h minus the initial condition of that, which is minus steady state. And if you can see that, I will have h steady state will cancel out steady state, is going to go equal to h. So if you're going to linearize h, you're going to get h. Okay, so don't worry about that, because if you forgot yourself for a moment, you're going to get the same answer. Okay, so that is something I just wanted to mention quickly. So now we have the square root of h for the valve, and we are going to take another example for a nonlinear term, which has the Arrhenius equation, and this term is e to the power minus e over rt. So that is a popular term, and this popular term, this is what you're going to do. So what is the nonlinear variable there? It is t, right? So the nonlinear variable is t, and later we are going to use this t minus steady state, right? So this term is equal to the same term at steady state, the same term at steady state, plus the derivative of that term, and the derivative of that term, if you do it by your own, it will be e over rt square e to the power minus e over rt. So that is the derivative of that term here, and since we are talking about a steady state, so it's at steady state, and this is multiplied by now the difference which is the t sitting inside this function minus the initial of that t, which is t minus steady state. Okay, so here I got it. So that is another approximation or linearization of an exponential term. So that is something else as well. Let's take a third example of how to linearize something that was very popular, where we have r is equal to kCa square. So we have dCa by dt, and in that dCa by dt term, I have this term here. Just to go at the beginning, so here we had the dH by dt term, and the nonlinear term was square root of h. Okay, and here in the Arrhenius equation we had dt by dt, and the nonlinear term was e to the power minus e over rt. And in this case, for the reaction, we have dCa by dt, and the nonlinear term that we want to deal with was the kCa square. And in this kCa square, if we just continue with it, I know that we have k here, so if you don't want to include k, because k is just multiplied by whatever I have here. So Ca square is equal to the same Ca square at steady state, plus the derivative of that Ca square, which is 2Ca, and that will keep it at steady state, into Ca minus Ca at steady state. Okay, into Ca at steady state. Okay, so it's that simple. So you can see like how we can deal with things here. If you want to talk about a reaction which has, for example, which has Ca multiplied by Cb, okay, like KCACB. Okay, so talking about that, and here I'm trying to linearize in terms of what I have as A. So what we are trying to linearize here, so we're going to have Ca steady state into Cb. Okay, oh my god. Okay, woo, what should I do here? What should I do? I'm stuck. Okay, here the linearization of two terms, which we have not only dCa by dt, we have dCa by dt one term, and we have another equation of dCb by dt. Okay, so it looks like that we have two equations here. And with dealing with the two equations, this is what we are going to do. So we are going to do them all in one step, linearizing those two terms. So we are going to say that both of them at steady state. Okay, so this is how it works. Plus the partial differential equation of one of them. Okay, it's like that, df by dCa at steady state into Ca minus Ca at steady state, plus the partial differential equation of the second variable, the second state variable at steady state, into Cb minus Cb at steady state. Okay, so it looks like now that is a linearized format. We just need to do this part here. So this will be equal to Ca at steady state, Cb steady state, plus if you take the differential, the partial differential with Ca, this will be Cb. Okay, so we are considering like the other one as a constant, so it will be Cb at steady state into Ca minus Ca at steady state plus here it will be CA at steady state into CB minus CB at steady state. Okay, so you can see how beautiful things are appearing here for us, and we can also linearize the term CA/CB. So now I think so we have the strong base that we know how to linearize things, and after knowing how to linearize, I think it's a good now it is time to do the deviation format, thing. And actually, if you look at the deviation format, we already have terms that look as a deviation format. See, this is a deviation format. This is a deviation format. And that is a deviation format. So all these are deviation format. Deviation format means what? Means the variable minus its steady state. And t minus t steady state, that means the variable which is changing with time minus the steady state. And here height as well, height minus steady state. Okay, great. So it looks like that things are fine for us. We already have deviation formats. But hold on, just to give you an idea of the deviation thing and to see the beauty of it. So of all what we have done so far here, that is for the first method, and the second method is exactly the same, which looks like that. Of course, the application is different. Okay, but it is exactly the same. In what sense? Is that what we have said, that f of x is equal to f of x naught plus I use now x naught instead of a. Okay, so I can keep it as x steady state. Okay, so it's any not value, or so f of x steady state plus, and we said what? We are going to take the first derivative, and the first derivative that we have here, I know I put a partial differential derivative, so it's df minus by dx at steady state into x minus x at steady state. So that is our formula here, right? I know this term here, you're saying that this is not partial differential equation because we only have x. You're right, I know that, I really know that, okay? But don't worry, because we are trying to get to a generalized format. This is the whole story. This is the whole story about it. So in this case, what we have here, it is the same equation that we have at the top there, except that we are trying to take this to the other. We are trying to take this term to the other side, and so we are going to have f of x minus f of x at steady state. So we take this to the left hand side, and we are going to be left with this on the right hand side. Okay, so what does that mean? It means that if I have my y minus y at steady state, so this is exactly in the deviation format. So I directly can do linearization. And this linearization is in deviation format. How did I know that this linearization now is in deviation format? This is because that this is already in a deviation format. And that's what makes it easier for us. So this is the second methodology. If you want to apply this for two cases where we have two variables, where we said that we have CA and CB in our term, right? And where we said that CA CB is equal to CA steady state plus into CB steady state plus the first derivative with x, the first derivative with CA, which was CB, so that was CB at steady state into CA minus C at steady state plus CA at steady state, that's the derivative, into CB minus CB steady state. Okay, so looking at that, so if you take this to the right hand side, and you're not going to repeat this thing, I'm taking this to right hand side and so on. You directly apply this, and you're going to get everything ready rather than calculating the first term here. So if you take this to the other term, this will be like CA CB minus CA steady state CB steady state. So now I have my deviation format, and it will be linearized because I already applied the linearization from. So this left hand side term is already at, okay, it's already at what? Is at its deviation format terms. Okay, beautiful. So we already have taken example to put in a deviation format. So what we are trying to do now here, okay, let's take an example. Okay, let's take an example. And examples, they always make things better because we live with examples in our life. We don't live just with equations, we live with the application of those equations. So we live with the real life examples. So if you can remember our tank, at last, after many lectures, we are back to our tank. Okay, and we were studying that how does height change with time. It's very important to know in that tank how does height change with time. And when we applied that equation, if you can recall, we had dm by dt is equal to fn minus f, and sorry, so that was not fn minus f, it was m in dot minus out dot, and then we took m as rho into v and v is a into h, so that was rho a into dh by dt is equal to, this will be rho n fn, density into volumetric flow rate, minus rho f, and then we cancelled out those density terms, and we had our final equation which looked like dh by dt is equal to fn minus alpha square root of h. And where did alpha square root of h come from? We said that f is equal to the CV into the delta p over specific gravity, and delta p is rho gh, and then we said that this is CV into rho gh over specific gravity, and then we said that all these terms can be considered as alpha, and we came up with the term alpha, which is going to be given in the exam most probably, and if it's not given, I'm going to give you this equation so that we can calculate it. Okay, so I'm going to give you the equation, don't worry. And this is equal to alpha square root of h. So what you need to memorize, at least, and for our problem, is f is equal to alpha square root of h. So this is the thing that you need to memorize. So we substituted here f is equal to alpha square root of h. So that was our equation that we had. So that was our equation. So what we are going to do now, we want to change that to the S domain. To do that, we need to do linearization plus deviation. Okay, so what I'm trying to apply here, I'm going to apply the linearization term. Now I'm going to do this in two methods. Okay, so I'm going to do the linearization. Oh my god. Okay, so I'm going to do the linearization. However, I'm going to do the linearization in two different methods, and these two different methods, that just keeps us more comfortable about which method we are going to be using. We already did the linearization for square root of h using Taylor series. So I'm going to say here, using Taylor series, I have square root of h is equal to square root of h at steady state plus the derivative, which is 1 over 2 square root of h at steady state into h minus h steady state. So this is what I have, and what I'm going to do here, I'm going to substitute square root of h into that term here. Substituting that term will provide me with the equation dh by dt is equal to fn minus alpha square root of h. I think I forgot the a. I always forget the a here, okay? The a here. Minus alpha into square root of h. Square root of h, if we multiply that, this will be alpha multiplied by I'll just multiply it. I mean, it's straightforward. It's just alpha, right? So you're going to multiply this at h steady state, okay, and that will be also minus alpha and minus alpha over 2 h at steady state into h minus at steady state. Okay, so this is what we have here. So that is our equation. That should be in a linearized format. Okay, so now is this linear? Is this linear or not? Yes, it is linear. And if you look at it, why it is linear? Because my h is to the power 1. What about these two h here? Okay, these two h here, they are constant values. They are constant values, so they are not considered as a variable or in a nonlinear terms. So we have this now linearized. We have this linearized format. So the second step that we are going to do here is to put it in a deviation format. And to put in a deviation format, this is the step that we are going to do here. So we are going to take our function at steady state. So we are saying that if the height is at steady state, everything is going to be at steady state. So if this height is at steady state, my fi is going to be at steady state, and my steady state will stay at steady state, minus alpha over 2 square root, and it will stay at steady state. And here it will be h at steady state minus the h which was already at steady state. Okay, so now you can see that there are some terms that will be cancelled out. So this term, which is at steady state, will all be equal to 0. Okay, actually even dh at steady state, which is the derivative of a constant, is 0, but we will keep it because we need to use that when we try now to subtract those two equations. So what we are going to do now, we are trying to find the deviation format, and to find the deviation format, we are going to subtract these two equations. Subtract the two equations, which shows like the thing at a normal, at a variable stage, minus the steady state stage. And if you do this, you will get the dh minus at steady state by dt is equal to fi minus fi at steady state. Okay, and then we come up to the term here. Aha, beautiful. If you can see these two terms will cancel each other. We are happy with this. And then we were left with the last term minus 0, which was already cancelled. So that will be minus alpha over 2 h at steady state value into h minus h steady state. I think things are getting really beautiful here, and we are getting our final shape of the equation. And now I think so we are about to take the Laplace, but before we do this, as for the sake of notations and making things easier for our life, we are going to define something new. H minus h steady state, we want to represent this as h prime. It doesn't mean derivative, it just means the difference. And here we are going to also have fi minus fi at steady state. We are going to represent this as fi prime. And this just makes our life easier to deal with our problem. So I'm going to rewrite this and say that this is dh prime by dt is equal to fi prime minus alpha 2, and this is multiplied by h prime. Okay, so now this equation is neater, right? This is like you can say that equation is neater. We like this. And what we need to do now, the step that we need to do here is apply Laplace. So that's it. Okay, here we are going to apply Laplace. So that's it. We have our equation which is linearized and it is in deviation format. Okay, so this is the equation in which it is linearized and put in deviation formats. Okay, beautiful. So that is what we have here. So when we apply Laplace, if you can remember, if you apply Laplace to the derivative term, if you just can remember, recall, I'll write this in red. So Laplace of y of t was the same y, and Laplace of a derivative dy by dt for things in deviation format, it will be s y of s. So that is what you need to remember here. Okay, so now we're going to apply Laplace. So this will be a, and this is a derivative term, so to be s h of s, and I know that it is in a deviation format, so I'm going to put the deviation format, is equal to fi s. So it's the same thing, right? Here I'm putting the same variable, but in this case I have a derivative, so I'm adding s. So let's continue. Minus alpha to h at steady state value into h prime, the same variable, so I'm going to put it at the same variable. So that is, now this looks like a math problem, the one that we solved in lecture number 12, I think so, the end of lecture number 12. It's like a math problem, and we are trying to solve using Laplace. So now we want to take h prime of s as a common factor, and if we take h prime of s as a common factor, this will be as plus taking this to the other side, so this will be plus alpha over 2 square root of h at steady state, so that is here, and my left hand side is left with the fi prime, fi prime. Okay, and so we just divide this, we bring this to the left hand side, and this is going to be h divided by fi is equal to, and I hope that everything is fine for me. Yes, it's equal to 1 divided by this term here, which is as plus alpha over 2 square root for the height at steady state. And great. What could I say more than that? We are having our final shape of the transfer function. So this is now definitely is in the S domain. And what do I have? I have a good relation between the output, and what is my output? It is the height, and the input, which is the input flow rate. So what I'm saying that if I change fi, what will be the value of h? So I think if I change fi from 20 to 30% opening, so that is 10% opening, and if we take this in the Laplace domain, it will be 10 over s, because there's a constant, so to be 10 over s, so I just multiply 10 over s with this right hand side, and I'm going to take Laplace inverse to find out that h in the time domain. So now we can see that everything is in algebraic format, and this is something else. So you can see that this term is in algebraic format, right? It's in algebraic format. It is easy that we have it. As a part of convention, if you want to do something additional, because this will help us a lot, is that transfer function, they do have a standard format, and this standard format, the standard format of a transfer function is like that: k over tau s plus 1. So the relationship, I'll write that again. So the relationship of output with the input The relationship is k over tau s plus 1. Okay, and you can add time delay, but in this case we don't have time delay, so we are not going to talk about time delay here. So we have k over tau s plus 1, and k is called the sensitivity and tau is called the time constant, and we're going to get to this later. Okay, because we need to study what do we mean by k and what do we mean by tau. It's simple. Sensitivity means hassasiyya, that means how sensitive is the process, and we're going to take examples, and time constant is how fast or how slow is the process, and we can know all this from this information that we have here. Okay, so this is what we have here as a transfer function. If you would like to put this in a standard format, putting it in a standard format, we need a plus 1, so we just need plus 1 in this side here. So that's the whole story. I make this term as plus 1, so I will divide it by the same term here, and because I will divide by the same term, so here it will be 1 over the alpha over square root of 2 into height at steady state, so that is the term that I have here. And if I divide this area over alpha over 2 height at steady state, and this will be, of course I will not forget s plus 1. Okay, so I have two terms here, and I'll just take this to the top to make it better. So this will look like 2 into the square root of height at steady state divided by alpha, and here it will be 2 multiplied by area into the square root of height at steady state divided by alpha into s plus 1. Okay, so this is what I'm having here, and this is what I would consider as the k value, the sensitivity value, and this is what I will consider as tau, which is the time constant. Okay, so I found both the sensitivity and the time constant. So that is how we take it to the S domain. This is how we take it to the S domain, and I think so that we had done a really good job now using the first method. Now what about the second method? Okay, what about the second method? Okay, can you tell us please with the second method how it's going to be? So we are going to solve everything now using the second method. Okay, and let's do that. Okay, so I think so it doesn't want to remove that blue pen from my face. Okay, so what do we have? We have our problem again, and our problem was dh by dt is equal to fi minus alpha square root of h, and there was an area here. So that was our equation, right? And we worked on the Taylor series on square root of h. Okay, so what you're going to do, this is what you're going to do. So we have dh by dt is equal to fi divided by area minus alpha over area into square root of h. So that is our equation. So it's the same equation here. And now we are going to apply the idea of doing the partial differential terms, in which we put it directly in a deviation format. So what we are going to say here, we are going to say what I'm going to write here. First, what function do I have here? I have fi and h. Okay, I have on my right hand side fi and h. So we will consider the inputs and state variables. Actually, we need to consider all inputs and all possible state variables. But for the meantime, we will just concentrate on what we have in front of our eyes. So in this case, we have fi and we have h. Okay, these are the inputs and the state variables that are sitting in front of our eyes. So what I'm going to do here, I'm going to say dh prime by dt is equal to the partial differential with dh into at steady state into h prime plus the partial differential term by dfi into fi prime. Okay, so this is what you are going to do, and this is I kept this directly. If you can see, I kept this term directly in a deviation format, because I already said that we take one of the terms of the Taylor series to the left hand side and it becomes in a deviation format, and directly the right hand side will be what? Will be also of course in a deviation format and in a linearized form by taking the different partial differential equations. Okay, that is nice. So what is the function that I'm going to derive here and I'm going to take the derivative of? It is the right hand side, so this is the function. Okay, so that is the function that I'm trying to have here. So it looks like that. So I'm talking about the function, which is a function of fi and h, is equal to fi over a minus alpha over a into square root of h. So that is the function on the right hand side. So let's take df by dh. df by dh here, so this is 0, the first term, because there's no h. We have an h here, so we're going to take the derivative. So it will be minus alpha, so this is my first term, minus alpha over a, and the square root is the derivative of height is 2 into square root of height, and we are dealing everything at steady state, so that will be at steady state. So that is my first term, df by dh into h prime. And then what is df by df, the d function by dfi? So that is the function, we derive it in accordance to fi, and the second term here will be 0, so I have fi here only, and if you take the derivative of that, it will be 1 over area. Okay, so it's like 1 over area constant multiplied by fi, so it will be only 1 over area into fi prime. Okay, that looks really beautiful. So that is one step. Did you see this? Just one step, doing both linearization plus putting it in a deviation format. It is that beautiful. And looking at it, I have something which is ready for what? Ready for Laplace. So my one step that I have applied, now I'm going to apply Laplace directly. And applying Laplace directly, this will be s, h of s for the derivative. And this is just a constant value. So I'm going to write this constant value. You just can put anything instead. A, B, C, whatever you want to put. This is just a constant value into h prime. And this h prime, because we are taking the Laplace, it will be the same variable in the s domain, plus 1 over a into fi in the s domain. Now taking this as a common factor, actually we'll get to the same equation. Okay, so this is what we don't need to do this again, but if you take a common factor of h of s, this will be s plus alpha 2a into the height at steady state is equal to 1 over a into fi at steady state. And rearranging things, we will have h over fi is equal to this 1 over area multiplied by 1 over s plus alpha over 2a at steady state, the square root of the height at steady state. And just rearranging this thing here, this will be 1 over as plus 1 over as plus area will cancel with the area, so that will be alpha over 2 height at steady state. And this is the equation that we just got at the above there. So this is exactly the equation that we got at the above. So it is exactly the same. And just to put it now in a standard format, I'm going to divide by this term here, and by dividing by this term I'm going to get 2 height at steady state divided by alpha, and here it will be 2a height at steady state divided by alpha, s plus 1, and that will be the value of k, the sensitivity, and that will be the value of tau, to have it look like k over tau s plus 1, which is the standard format of a transfer function. Great. So we had shown you that how you can apply the two methods, and I will go through the second method again because I want a bit quickly through it. So the second method, what does it say? It says that now this is the equation of dh by dt, which is f over I over a minus alpha over a into square root of h. And what I'm trying to do here, I'm trying to put it in a deviation format. I'm trying to put this equation in a deviation format and the linearized shape in one step. How do I do this? I say that this is my function. What I'm trying to do here, I'm trying to take the derivative of it by h into h prime, and then I'm going to take again this function derivative with fi prime. So I'm simply taking the derivative with the all state variables plus the derivative with all inputs, and I have only one state variable and one input, and this is why I have only two terms here. And the left hand side will be directly in a deviation format, okay, based on the Taylor series that I have explained earlier. So you just take the derivative with h, you get this term. You just take the derivative with fi, you get this term here, and then you take the Laplace, where dh prime by dt becomes s prime of s, and when h prime becomes h prime of s, and when fi becomes fi of s. I will just put the prime here. Okay, sorry for that. So I need to put that in white. Okay, and then rearranging those stuff, I'll just rearranging, taking common factor and then taking fi into the bottom here, and we get our final shape, which looks like that. Well, these are our two equations. You need to keep it in the final shape if we are requesting to find k and tau. So when we say find k and tau, you need to put it in the you need to put it in the standard form. In the standard, I'll write that totally in the standard form of the transfer function. However, if it did not require us, if it did not ask to find the standard form, just to find the transfer function, finding the transfer function, it's enough to stop at this step. You don't need to put it in the standard form because this is a standard, this is a transfer function as well. Okay, and both of them is fine to work with. So this is what we have, and we have solved for. And actually now, if you are waiting to change that into the time domain, it's very easy, because this looks like what? This looks like 1 over s plus a, right? So if you just divide by this area, this looks like something I'm going to show it to you. We are going to solve this later, of course, but just for you to get like happy with it and see, this looks like something like that, right? If you remember, we had, I'll do that in blue, I think so. Okay, sorry for that. So if I do this in blue, so 1 over s plus a, and having it 1 over s plus a, taking the Laplace inverse of 1s plus a, if you can remember that, this will be e to the power minus at. So the answer of this problem that I have here will be something like e to the power minus at. Okay, because I have some kind of a constant at the top over s plus a. So this constant that I have at top will go outside, because this is a linear operator. So I'm going to have some kind of a whatever term here, a constant term. I'm going to call this like C1 or whatever, a constant term, into e to the power minus e over at. Okay, so this is this is what we have here. So this is what we have here as a function, which means that if I'm going to plot my height, if I'm going to get the answer, this is the answer of my height. So we had it as dh by dt. Now I found h after taking the Laplace inverse. If I have height with time, because this looks like an exponential with a negative exponential term, it will go something like that. And this is the real output of how the height would look like. So I think so we can conclude lecture 14. It had been very interesting, and we have taken today two methodologies of how to do the linearization and putting it in a deviation format, okay, and to find what? To find the transfer function. If we just go to the top there, this is where we had started, and when we started, what did we say? We said that we have the model equations of dh by dt, dca by dt, dt by dt, dp by dt. We solve now the example for dh by dt, and we are going to solve the examples again for dca by dt. So what we want to have this model equations that we see at the left here. We want to take the Laplace to find transfer functions. However, we cannot do this directly. We need to have this time domain. Usually it is non-linear. And to make it linear, we need to do the linearization, where we can do this in two steps of linearization plus putting it in a deviation format, or we can do that in one step where we do both linearization and deviation. If we do this two steps or that one step, which are two methods, we are going to then apply Laplace, and by applying Laplace okay, you're going to get your S domain in the transfer function. And this transfer function that we have, this transfer function, it has a standard format. You can keep it in a standard format or not, depending if they want to find k and tau. And if you have the standard transfer function, what you need to do is you take the Laplace inverse, and by taking Laplace inverse, you're going to get the solution. Which is the h term. And in our case, we had something like a constant into e to the power minus at. And we did not find what is a or c1, but we are just saying that it will look something like that, and definitely is going to have a shape which looks like that. Okay, and this is the h, and this is the time, and it goes to a steady state value. Okay, it's like I'm saying that this height, when I did an opening, I did change the fi. I did change fi here. I did change fi, the valve, from one value to another value. It shifted from one steady state value to a new steady state value. Okay, so this is what it means. And when it went to a new steady state value, it just stayed there. Okay, so that concludes our problem. I hope that you have enjoyed our lecture 14, doing the linearization and putting in the deviation format. All the best guys and girls, and I hope that you have a smiley face and you know that things are very nice here, and all the best luck. Thank you very much. See you soon.